Hi, this is 12.1, an introduction to sequences and series. Throughout this video, you may want to pause your video just to take some notes on things, just to write down anything that I'm going through too quickly. So feel free to use that button as you go. The first thing to define is a sequence. A sequence is just a string of numbers. Typically, we will look at integers, but we can have anything as our range. Our domain, though, is going to start at 1. So the first term is like an input of 1, and then you output whatever that term is. And there's some specific notation that we need to look at. The first term is going to be denoted as, and this is called a subset right here, this little 1, and it's called A1 or A sub 1. And then A sub 2, A sub 3, A sub 4. Just a subscript just to kind of keep those things straight. It's kind of like, if you remember, a coordinate back when we had x1, y1, and then we had a new coordinate which was x2, y2, and you could continue this pattern x3, x4, x5. All right, well, our input now is just going to be 1, 2, 3, 4, 5, 6, 7. It's the term. Like, which term is it? The first term? Is it the 10th term? Is it the 100th term? And then the range is just, okay, well, whatever that is, it's A sub 1 if it's the first term. If we want the 100th term, I would say A sub 100. There are two types of sequences that we will study. There's a finite sequence, which has a limited number of terms, a countable number of terms, and then infinite continues forever. And the main way that you'll see those denoted is with the dot, dot, dot. If it's a finite sequence, it will just stop. It will end. There's nothing that continues. An infinite sequence can look very similar, but will have that dot, dot, dot at the end, implying that it continues in the same pattern forever. That's what that dot, dot, dot represents. So let's see if we have sequences. We'll get to series later. A sequence can be written as a rule, and here's an example of a rule. We've got A sub n, that's the general term. We always use n when we talk about sequences. A sub n is equal to 2 to the n plus 1. So whichever term you want, and this is called an explicit rule, whichever term you want, if you want the 100th term, well then you plug in 100. All right, so I'm just going to have you list a couple here. The first term. Well, first term would look like this, A sub 1. What does A sub 1 look like? Well, it's 2 to the 1 plus 1, which is 2 to the second, which is 4. So all you're doing is you're plugging 1 in for n, and it's an explicit rule. You can plug in 1, you'll get out the term. If we want the 100th term, we could plug in 100, we could get it out. So we could continue like this. The second term, A sub 2, is 2 to the second plus 1 up there. Okay? So it's actually 2 to the third, which is 8. And what you'll notice is that because we have a base of 2 here, we're going to be doubling. So if I go to the third term, it's 2 to the 3 plus 1, which is 2 to the fourth, which we know is 16. And it continues, the pattern continues, but this is how we will write explicit rules when it comes to sequences. We are looking to just be able to plug in an n value to get out the term. So as much as we could say, all right, I know the next one will be multiplied by 2, all right, that's called a recursive pattern, just taking a look at the previous term, going to the next term. The problem with that is if we need the 100th term, if we try to continue this pattern, we would need to find the 99th term. And in order to find the 99th term, we need to find the 98th, and so on, back, 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 back. So what we do instead is we have explicit rules like this. So we could say A sub 100, okay, is 2 to the 100 plus 1. And that's too big a number to calculate, but we could certainly do it if we had to, right? So your task is going to be to write rules, and that's really the hard part. We'll have some shortcuts when it's specific types of patterns, but here's an example of one. We've got 1 going to 4, going to 9, and then going to 16. First thing I look for is if there's any noticeable pattern when it comes to how much is it going up by. this one goes up by 3, and then this goes up by 5, and then this goes up by 7. Even though that there is a pattern there, it's 3, 5, 7, most likely the next one would be 9. That's still not an easy pattern to describe. When the amount goes up, changes, it just doesn't work. Then I decided to say, okay, is there any pattern for multiplying? Okay, well, we're going to multiply by 4. All right, well, then here we'd have to multiply by 4 9/4, okay? And then here we'd have to multiply by 16 over 9. It just doesn't appear that there's any pattern there at all when we're multiplying. But if you look closely at these numbers, you'll recognize that 1 is 1 squared, and 4 is 2 squared, and 9 is 3 squared, and 16 is 4 squared. All right, and so we've got a pattern here that's pretty noticeable. This is the first term, this is the second term, here is the third term, and this is the fourth term. So it seems to me, and this is n, it seems to me that basically we're taking n and we're squaring it. So our general rule for the nth term, a sub n, is equal to n to the second. Take your n value and square it. So whatever term, if you want the 100th term, let's say we want a sub 100, well then you'd be asked for 100 squared. These patterns are the ones that we'll be studying in this class. This is called arithmetic. We'll be studying these in 12.2. We are subtracting 1.1 each time. We're subtracting 1.1. So the pattern kind of starts at 6.6. That's our first term. And we subtract 1.1 each term, right? So we would think maybe 1.1 times n. But remember that 6.6 is the first term. So when we're writing our rule, if we've got n and we just leave it as n, when you plug in 1, you've already subtracted 1.1, and we don't want that. On the first term, we want it just to be 6.6. We don't want to subtract anything. So instead of trying to manipulate that around, I'll just simply say, you know what? Do 1 less than what you think. So if it's the first term, if you plug in 1, we won't be subtracting 1.1. Because if you plug in a 1 here, 1 minus 1, that's going to be 0, and you'll just get 6.6. Okay? The same thing kind of works here. What are we doing to get the next term? Well, we're multiplying by 2. All right? But because this isn't the 0 term, this is the first term, first, second, third, fourth, you may want to say, okay, well, a sub n, all right, and we should actually have a correct notation up here now. Maybe you're going to say a sub n is 3 times 2 to the n. Well, again, we run into that problem where if you don't subtract, if you don't do n minus 1, then you're not going to get that first term to be accurate. Because when you plug in a 1 here, if we were to plug in a 1, and if we did not have the n minus 1, if it was just n, it'd be 2 to the first, and be 3 times 2, that's 6, and that's not the first term. So you kind of have to delay that multiplying by 2 for one term, because we're not multiplying by 2 on the first one. The other way that you could manipulate around that is to go backwards. Like, what would be the term back here? What would be the 0 term? Well, it's 1.5, right? Half of 3. So you could write it like this, 1.5 times 2 to the n. And that would work so that you are actually on the first term going to multiply by 2. I don't particularly like that method. I like to use the numbers that I see, and this is the formula that I will stick with. So that basically is what a sequence is about in the notation. We'll get into more specifics on the next lesson. We are now also going to look at series. So a sequence is just commas. All right, comma, comma, comma. All right, moving on. The series is addition. So if we take those commas and now we change them to addition sign, to adding. So we want to add something up. You again can have a finite series and an infinite series. Now this right here would have no sum, because you're going up, up, up to a million, infinity. You can't add that up. A finite series, we can always add that. We abbreviate sums with summation notation. That's what this is called right here. This is called sigma, or summation notation. And it takes a little bit getting used to, but it's pretty easy once you break it down. And let's see if you can kind of see, like, okay, we've got 4 terms, right? You're summing from the first term to the 4th term. And here's the rule. On the next one, you're summing from the first term to infinity. So the first term up to, okay, you're summing up to infinity, and here is the rule. I've got a more detailed explanation of that. You're going to want to pause it, take a look at this, and make sure that you understand the 3 pieces. This is a sigma. The first value on the bottom is where your starting term is. The last value, the top value, is the last term. Now remember, it's term, and then you always have to have the rule so people know, what is exactly happening. So we're going to see if we can write this in summation notation. The first thing that we need is a rule. So what do we have happening here? Well, we're adding 3 each time. So very quickly, it's 4 plus 3. You may think, okay, it's times n, but remember we got to have the n minus 1. And it will simplify 4 plus 3n minus 3. Your formula becomes 3n plus 1. So there's your rule, but now we need to have the sum. We know that we're going to start, and we usually use I. We're going to start at 1. What are we going to go up to? I'm not really sure quite yet, but here's our rule, 3i plus 1. So we got to figure out what term is this. You're not going to sum up to 46, because 46 is the value, not the term. So which term is this? Well, we can just plug that in right here. 3n plus 1, and we can set it equal to 46, and we can solve. Subtract 1, divide by 3, n is 15. So you're summing up the first 15 terms. And that's how we can take this long sum and write it using summation notation, just a shortcut abbreviated version. Question B is an infinite. This one's a little bit easier. So now we are looking at our summation notation. We're going to start at 1. That's always how we're going to do it. And we're going to sum up to infinity. And this is actually one that we could sum because it does approach 0. And so the sum is not going to be going towards infinity. We'll talk more about that later. But we have to write the rule here. This is 1 over 1. And then this is 1 over 2 cubed. And then this is 1 over 3 cubed, and then 1 over 4 cubed. And I bet we could go back and say that's 1 over 1 cubed. This is the first term, second term, third term, fourth term. So it appears that we are just going to take 1 over n to the third. The last question I have for you here then is just actually using one of these sums. This one starts at 3, uses k. There's no problem. We just stick with I usually, but it really doesn't matter, the variable. So what this is telling us is that you need to plug in 3. You got 2 minus 3 times 3 would be 9, so 2 minus 9 is negative 7. All right, and then you need to plug in 4. Plug it in right there. 2 minus 12. 2 minus 12 is negative 10, so we're adding a negative 10. Plus, then you sum to 5, plug that in right there. 2 minus 15 is negative 13, and you stop. Because this number up here tells us that we need to stop at 5. Add those things up, and we get a negative 30. And that would be your answer. That would be your sum.